Module 4, Replication and Scaling. Overview of replication and its benefits. Replication is the process of creating and maintaining copies of a database or parts of a database in multiple locations. In the context of databases, replication is often used to improve availability, scalability, and data durability. Replication allows for the creation of one or more copies of a database, known as replicas or standbys, which can be used for various purposes, such as 1. High availability. Replication can provide increased availability of a database by allowing for automatic failover to a standby database in case of a primary database failure. If the primary database becomes unavailable due to hardware failure, software issues, or other reasons, a standby database can take over the workload, reducing downtime and ensuring uninterrupted access to the database for applications and users. 2. Load balancing. Replication can distribute the workload across multiple database replicas, which can be used to balance the read traffic and reduce the load on the primary database. This can result in improved performance and scalability, as read-heavy workloads can be offloaded to read replicas, freeing up resources on the primary database for write operations. 3. Geographical distribution. Replication can be used to create copies of a database in different geographical locations, allowing for improved data locality and reduced network latency for users in different regions. This can be beneficial for applications with global user bases, where data needs to be replicated across multiple regions for improved performance and user experience. 4. Backup and disaster recovery. Replication can be used to create off-site copies of a database, which can serve as backups or replicas for disaster recovery purposes. If the primary database becomes unavailable due to a catastrophic event, such as a data center failure, natural disaster, or other unforeseen circumstances, a standby database can be used to restore the database to a previous state and ensure business continuity. 5. Data consistency and durability. Replication can ensure data consistency and durability by maintaining multiple copies of the database in different locations. Changes made to the primary database are replicated to standby databases, ensuring that the data is consistent across all replicas. In case of a failure or data loss in the primary database, the standby databases can be used to recover the lost data. Overall, replication provides several benefits in terms of improved availability, scalability, data durability, and disaster recovery. However, it also requires careful planning, configuration, and monitoring to ensure its effectiveness and reliability. Different databases and replication technologies may have different features, capabilities, and limitations, and it's important to thoroughly understand the replication options available for a specific database system and choose the appropriate replication strategy based on the requirements of the application and data environment. Regular testing and monitoring of the replication setup are also crucial to ensure its reliability and readiness for handling unexpected events. Logical and physical replication. Logical and physical replication are two different approaches to replicating data in a database system. Here's an overview of each. 1. Logical replication. Logical replication involves replicating changes to data at the logical level, such as replicating changes to individual rows or statements that modify data. It captures changes to data in the form of logical statements, such as insert, update, and delete statements, and replicates these statements to replica databases. Logical replication typically works at the SQL statement level and replicates changes based on the structure and content of the data, rather than at the physical level of the storage. Advantages of logical replication include the ability to replicate changes selectively based on specific tables, columns, or conditions, and the ability to replicate changes across different database versions or different database systems. It also provides more flexibility in handling data transformations or filtering during replication, as the changes can be processed and modified at the logical level before being replicated. 2. Physical replication. Physical replication involves replicating changes to data at the physical level, such as replicating changes to database files or blocks. It captures changes to data at the level of the physical storage, such as changes to disk blocks or pages, and replicates these changes to replica databases. Physical replication typically works at the level of storage, and changes are replicated based on the physical location of the data in the storage. Advantages of physical replication include faster replication performance and lower overhead, as it operates at a lower level of the storage and does not require processing of individual SQL statements. It also provides an exact replica of the original database at the physical level, which can be useful for scenarios where an exact copy of the original database is required. In PostgreSQL, a popular open-source relational database management system, both logical and physical replication options are available. PostgreSQL supports logical replication using features such as logical replication slots and logical decoding, which allow for replicating changes at the logical level based on logical statements. PostgreSQL also supports physical replication using features such as streaming replication, which allows for replicating changes at the physical level based on changes to database files or blocks. The choice between logical and physical replication depends on factors such as the specific use case, performance requirements, data transformation needs, and database system version compatibility, among others. Scaling PostgreSQL, shading and partitioning. Scaling PostgreSQL, like any other database system, involves various techniques such as sharding and partitioning. Here's an overview of each. 1. Sharding. Sharding is a technique used to horizontally partition a database across multiple nodes or shards. Each shard contains a subset of data and operates as an independent database. Sharding can be done based on various criteria, such as range-based partitioning, example, data ranges based on keys or timestamps, hash-based partitioning, example, data hashed to determine the shard, or other custom criteria. Advantages of sharding include the ability to distribute data across multiple nodes, enabling better scalability and performance for read and write operations. It can also help in achieving higher availability, fault tolerance, and load balancing by distributing data and workload across multiple shards. 2. Partitioning. Partitioning is a technique used to divide a table into smaller, more manageable pieces, called partitions, based on a specific criterion, such as a range of values, a hash value, or a list of values. Each partition is treated as a separate entity with its own storage and indexing, but it is logically part of the same table. Advantages of partitioning include improved performance for certain queries that can benefit from accessing only a subset of data within a partition, reduced storage requirements by eliminating the need to store all data in a single table, and improved manageability for large tables. Both shading and partitioning are effective techniques for scaling PostgreSQL databases to handle large amounts of data and high levels of concurrent users. The choice between shading and partitioning depends on factors such as the specific use case, performance requirements, data distribution needs, manageability, and complexity considerations, among others.
Thanks for watching. For more information, like, comment, and subscribe our channel.